All right, as I said, our first speaker today then is Jonah Prosick from Novateur Research Solutions, speaking to universal identification of biological and chemical constituents. Jonah?
Hi, everyone. Yeah, so I'm Dr. Jonah Prosick with Novateur Research Solutions, and I'm going to be presenting my work here. I'm the PI on this work, where we are basically extending existing detection technology with some robust deep learning models in order to deal with unseen novel threats that can in both the biological and chemical realm. So what is the problem that we are trying to solve? Well, biological and chemical threats are exceedingly dangerous. They can be invisible to the eye, as well as transmissible among different people in the biological realm, as well as being very hazardous to health. Things such as nerve gases, anthrax, even just byproduct of normal combustion of everyday objects is going to have threat or chemicals that are hazardous to human health. They also require specialized equipment to detect as well as synthesize these threats typically, and these threats can be novel to detector systems. So that's what we want to solve, is we want to take away some of the specialized equipment, and we want to also be able to detect novel, unseen threats and tell you what they are or most likely are. So who can benefit from this? Anyone in the national security realm. You can think of it as any airport or seaport, train station, really any public venue that could be a potential threat. You can think energy sites. So we would obviously probably be of interest to something such as TSA, U.S. Customs and Border Protection, or even law enforcement. If say you're doing a raid on a lab and you want to know if it's safe to go in there and collect evidence, you can use our technology and make sure that there's nothing down there that will negatively impact officers. Same goes for EMTs and firefighters as well. So what are the current state-of-the-art methods that we're trying to improve upon? So this is an example, a very non-exhaustive list of the existing technologies out there. And they all have basically two things in common. So they all utilize a single spectral technique. So in every case, they're shooting some form of radiation at it, and then they're measuring what comes back, and they're telling you what they think the unknown is. So in the examples I'm showing you, there's fluorescence, there's mass spec, Raman, FTIR, but they all use just a single one of these different techniques. And then what they do is they rely on these things called spectral libraries. So they have a pre-compiled list of all the threats that they possibly can measure. And then they will compare an unknown sample to that and tell you what the most likely chemical is that they just detected. So this is known as library matching, where they have their extensive library of known threats, and they will take the unknown and they will compare it to all the spectra in their list, and anything that comes up as a good match, that is considered a positive identification, and they can assume that that is in the sample. So there's a few different problems with this. Number one is you're not going to be able to have every spectra of every chemical out there. It's just not possible. Chemical space is incredibly large, and right now we are covering a fraction of a percent possibly of the possible threats out there. It requires a suitable spectra. So this is exactly what I was kind of getting to. It can't, so if there's like a difference in the chemical structure at all, say you have a drug and it's seemingly like it's fentanyl, but it's got a couple other peaks in there, so you can't make a positive identification. Our system would be able to deal with the structural difference and tell you that, yes, it's most likely a fentanyl derivative, and it's probably got these modifications as well. And so it's susceptible to experimental artifacts, including instrumentation differences, concentration differences, and noise. And so this is really what we are aiming to improve upon, is this library matching algorithm. So what do we need for our technology? We need it to be accurate, no false positives, no false negatives, or very, very few at a minimum. We need it to be flexible, where it can handle unseen agents, something that's never been measured before. We need it to be very speedy. We want these detections in real time so that we can deploy preventative measures as soon as possible. And we need it to be portable. So very fast, easy to use, and can be used on any basic technology like a laptop. Yeah. So what is our system? Our system is a software backbone that is able to detect chemical and biological agents using machine learning methods at near real time with any substance. It can be brand new or something that's been measured before. And we can integrate information from multiple different measurements. So this means if we have set up a measurement device that detects or that can give you an FTIR readout as well as a mass spec readout of an individual sample, we'll be able to integrate the information from both to produce a more accurate and reliable identification. So we identify the complete chemical structure as well as any related molecules that are known and their properties. So this system can technically work with any spectral measurement. Right now we have it, we're currently developing it towards FTIR and mass spec, but we can extend this to any spectral measurement of any type, provided that there's enough training data for us. And so you can see below is a diagram of what we do, where we have our data collection here. You can see we get an FTIR and mass spec readout from our sample. We use mixture deconvolution. This is a little separate model that basically separates out the individual components of the measurement so that we have pure samples to work with. These are then fed into our chemical structure encoder decoder model, which produces the most likely chemical structure from a given spectrum, as well as the functional groups present. And we integrate this with a large library. Think everything in PubChem, so around 113 million molecules or so. We have all of that in a database that we then search against and find the closest matches. So what can this be used for? So live monitoring, say you have an energy site or a base somewhere or a public event, any form of public site really, and you want to be able to make sure that the public is safe. So you can see here, this would be an example of what our UI might look like. So we would have two measurement stations, and if you look at our little map over here, we have 1 and 2 for our different stations, and they would have scheduled measurement times. So in this case, we're thinking of them as kind of these are measurements done at a airport or some form of station where people are coming back and forth, and there's some security already. And so what's happening is we're taking measurements of people's items or anything suspicious, and we can see that at 10, these are individual measurements, these gray boxes. So at 10 and 2 seconds, we get a measurement with these 3 chemicals in it, and we can see that the gray box means that they're pretty much clean, and we get the complete chemical structure from that as well. But then at 10:30, we see this nice red, and that's actually the structure of fentanyl in there. So we detected that there's some very bad drug in our mixture. And so, we made a positive identification on it, and we can move forward from there, whatever needs to be done to deal with the threat. And so we can also do this remotely, where people are given measurement devices in the field, say it's this handheld gas FTIR, and say you're going into a lab and you're trying to identify if these powders, unknown powders on the counters are something dangerous. And so, or I guess in this case, a gas FTIR isn't too. So don't think of it as powder, but it can be any phase, really, solid, liquid, gas. And basically you're taking measurements and you're creating reports back in real time if there's anything dangerous in the mixture of what you're measuring. And so you can think of this as you're helping different teams and individuals. They're getting real-time readouts if something is wrong and they need to get out of there. And so this can help us minimize damages to equipment, prevent casualties, and any preventative measures we can take, we can do those as soon as possible. So what do we actually get out of this? So we get the complete chemical structure from our spectral measurements. So in this case, this was the predicted structure, and then we get the predicted functional groups as well. And these are actually independent of each other. They're not derived from one another. And this is to make sure that we keep things as reliable and robust as possible. And then we identify the chemical by both its matches of the complete chemical structure and its matches by its functional groups, so the things that are most chemically active. And so we can see here all of our matches are fentanyl related, as this is once again the fentanyl chemical structure. And same thing with our functional groups, where maybe our chemical structure isn't exactly the same, such as for norfentanyl, but the functional groups are very close. And so finally, what we'll get out of this is a final classification. Is this an illicit drug? Is it an unknown? And we'll also get a certainty score of how reliable our predictions are to make this much better for users that don't just get a blank, it's probably this. So important features of this is that we integrate information for orthogonal measurements. So as I said before, we can incorporate multiple different measurements such as FTIR and mass spec together. We can encode chemical space with functionally and structurally relevant methods. So this allows us to make IDs on unknowns much more reliably because we do structure it by functionality inside our chemical space encoding. And then when it's also lightweight, efficient, and modular, so we can do this in real time on a laptop or anything that's kind of size, weight, and power constrained, we can make that work as well. And then finally, we also have property prediction. So we can identify threats far from any unknown just from its functional group prediction. So because those are going to be in common even if the complete chemical structure is relatively unknown. So the benefits over the existing technology, the library matching that I mentioned at the very beginning, is that once again, we can integrate information from multiple sources, and we're able to detect and identify novel threats, something that library matching is very unable to do unless it's a very, very minor modification, as well as a property prediction of the measured substance with our functional group prediction. So the current status of this is we have 9 months remaining. I think it's 8 months now. I wrote this a little bit ago. And we're currently searching for spectroscopy component manufacturers to partner with so that we can actually get it, we can get the spectral data out of the machines in an easier method. I think right now we're limited to using USBs and yeah, it's not real time. So that's something that we're working on. And we're also actively searching for any phase 3 partners. So if you have any use cases at all, this is a very, very general technology in that it can be used for wearables, non-wearables, you know, environmental gases, powder sampling. Yeah. So if you have a use case, please let us know and we'd love to talk to you about it. A little bit more about us at Novateur Research Sciences. We are pretty much our focus is integrating deep learning models with sensor systems to basically give our systems the ability to make decisions for themselves, make it smart and autonomous. And we've done this for the Army, ONR, quite a few different agencies with the DoD, Department of Transportation. We've worked with just about every 3-letter agency you can think of. And we're excited to continue our work with DHS. Yeah, so just to touch back with what we would like from you guys, if you guys are interested, is the type of threats that are important to you. Would you mainly be interested in gas detection, powder detection? And we can adapt our technology as needed. Existing, what do you currently use and how can we improve upon that or integrate their system into ours so that we can make even better prediction? And then the type of information you need from these measurements. Do you want the full chemical structure? Do you want functional groups? What exactly do you want? And then finally, reliability, how we're going to go about that. And we'd love to hear from you guys, real world testing that we could possibly perform to ensure that our system works. And then finally, so yeah, we need more funding to get this off the ground. We're in a good place with it right now. We'll have a live demo of it either late this year or early next year. And we'd be excited to show everyone that if you're interested. So yeah, if you're interested, please reach out to us. I have my email there at the bottom. I don't know if these slides are shared with you guys, but I hope it is. So thank you guys. I appreciate your time and hope to hear from some of you.